Alright, so welcome back, CSE 215, Lecture 2B. So let's start looking at set operations, other ways we can combine two sets. So throughout this, we're going to let A and B be sets. And we're going to define the following operations. So the union of A and B, and we write this as a U, and a B, and this is equal to the set of all elements X, such that X is in A or X is in B. The intersection we write as A with an upside down U or a cap. A intersect B equals the set of all X, such that X is in A and X is in B. We define two sets to be disjoint if the following is true: A intersect B is equal to the empty set. In other words, there's no element in common between A and B. So back on our Venn diagram, this here represents the intersection of sets C and H. It's all the things that are in C and also in H. If we draw a heavy outline like this, that would be the set C union H. It's a set of all things that are in C or in H. It also includes things that are in both C and H. Nothing wrong with that. If something's in both of these sets, well, it's certainly in A and it's certainly in B, so it's in A or B, it's still in the union. So this whole thing here would be the union, this little piece here would be the intersection, and V and C would be an example of disjoint sets because there's nothing that's in C and also in V, so their intersection is the empty set. We can also define subtraction, A take away B, or sometimes this is written A with a backslash and a B. So A take away B equals the set of all X which are contained in A and not contained in B. So that one takes a little bit more thinking about. It's a set of things that are in A but also not in B. So if A equals the set 1, 3, 5, 7, 9, and B equals the set 2, 3, 4, 5, A take away B is everything that's in A but not in B. So here's the element 1 that's not in B, so that's part of A take away B. Here's the element 3 that's in A, but it's also in B, so it's not going to be in A minus B. Here's a set 5 that's also in B, so that doesn't go in. But 7 and 9 are contained in A and not contained in B. Does the 2 affect anything? Absolutely not, right? We're looking at elements in A that are not in B. So if you like, you list the elements in A and then you cross off anything that you find in B. We cross off the 3 and the 5, and we're left with 1, 7, 9. If we went the other way, B take away A, it's the set of things in B that are not in A, so that includes the number 2 and the number 4, but 3 is in A and 5 is in A, so those are not in B minus A. So that takes a little bit of getting used to. This is called the complement of B in A, right? A minus B. All right. So here's a fun fact that we'll work out on the board. If you take the cardinality of A union B, and again, A and B are finite sets. Anytime we do cardinality for now, we're going to assume the sets involved are finite. So the cardinality of A union B is less than or equal to the cardinality of A plus the cardinality of B. And that's fairly intuitive, I think, right? The number of things that are either in A or in B cannot be greater than the number of things in A plus the number of things in B. Because anything that's in here has got to be in either this or that. So the number of things in here and the number of things in there puts a bound on how many things could be in both. But in fact, we're going to see that we can make this into an equality as follows. Right? Take the number of things in A, add the number of things in B, subtract the number of things that are in both. That gives us the number of things in the union. So we'll work that out on the board in a homework exercise. All right, so we've defined A take away B. In the special case where A is the universal set, the universe take away B, we just write with a special symbol B bar. And that's just the complement of B. And what does this mean? Well, from our prior definition, right, A take away B is a set of things that are in A but not in B. So the universe take away B would be the set of things in the universe that are not in B. Well, everything is part of the universe, right? Assuming that B is part of the universe. This is simply the set of things in the universe that are not in B. So B is a collection of things. The complement of B is the collection of everything that's not in B. So in a Venn diagram, if this is our set B, all this stuff out here, that's the complement of B. So that's a special case of complement. That'll be useful sometimes. All right, so this brings us to the notion of set identities. And if you've done Engineering 250, some of this should be starting to ring a bell, perhaps. And identities, in particular, will start to look familiar, I think. So, again, we're going to assume A and B are sets and U is the universal set. So here's some things that are always true. A intersected with the universal set is equal to A. A union the empty set is equal to A. And we'll do some homework questions to explore these with particular examples. A union the universal set is equal to the universal set. And A intersect the empty set is equal to the empty set. A union itself is equal to A. A intersect itself is equal to A. If we take the complement of A and we take the complement of that complement, we get A. A union B is equal to B union A. A intersect B is equal to B intersect A. A union the set B union C is the same as the set A union B union with C. And none of these are terribly surprising if you work through particular examples, right? This is a collection of things that are in A or B. This is the collection of things that are in B or A. Well, it's exactly the same, right? This is the collection of things that are in A and also in B. This is the collection of things that are in B and also in A, right? That's exactly the same thing. I just said it a little differently. This is the set of things that are in A or in B or C. This is the things that are in A or B or C, right? I mean, it's exactly the same meaning. So these are fairly obvious if you think about them and you throw some particular examples. We'll do some homeworks on these. These are perhaps a bit less obvious. A union, the set A intersect B, is just the same as A. And A intersect the set A union B is also equal to A. This is something we call absorption. A union A bar is equal to the universal set. A intersect A bar is equal to the empty set. What does this mean? This is the set of all things that are in A or not in A. Well, that's everything, right? It's either in A or it's not in A. This is the set of things that are in A and also not in A. Well, is there anything that's in A but also not in A? No. So the collection of things that satisfy that is the set consisting of nothing, the empty set. And here's one that'll totally flash you back to digital logic. If we take A union B and we complement it, that's the same thing as taking the complement of A and intersecting with the complement of B. And if we take A intersect B and complement it, that's the same thing as the complement of A union the complement of B. And in case you don't remember, these are called De Morgan's theorems. And there's names for some of the others of these, right? This is the commutative property, this is the associative property, and there's fancy sounding names for these properties up here. But these are all things that we see in digital logic. And there's a reason for that, right? It's not just a coincidence. There's actually a strong parallel between what we do in digital logic and what we do in set theory. They're very much the same thing. All right, so next set of lectures, we're going to start looking at how we can prove things like this, or things like this, or things like whatever we want, right? Any kind of statement that we write about sets, where we say some set of operations here equals the same set of operations over here. We're going to look at ways that we can prove that. And we can prove that either by using these identities and doing some algebra, or by using something called a membership table. So that's where we'll start off next time.